Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. For part number 4, we will discuss about the Otto cycle. So in terms of content, we will discuss about the process involved, the equation that involved for each process, and also the example for the Otto cycle. Okay, now it's about introduction to Otto cycle. The Otto cycle actually is the thermodynamic cycle for spark ignition engine or for petrol engine, and we can apply the Otto cycle for both 2-stroke and also 4-stroke spark ignition engine. So the founder of the cycle is Nicholas August Otto, as shown in the figure. In terms of period, he was born in 1832 and passed away in 1891, and he is a German nationality, and during that time he is an engineer. Okay, so in terms of engine development, Otto already developed or built four engines during his period. First, in 1861, he built a copy of Linnoy's atmospheric engine, where he used different kind of fuel to the engine. Okay, next, in 1862, he developed a 4-cycle compressed charge engine. However, the engine was failed. Next, in 1864, he developed the first successful atmospheric engine, as shown in the figure. So the figure shows the Otto atmospheric engine. Okay, and the last one, in 1876, he built the 4-stroke compressed charge engine, where this engine is referred as the Otto Cycle engine. Okay, so the last engine that developed in 1867, that referred as Otto cycle, actually is the basic of modern spark ignition or petrol engine that we use today. Okay, as shown in the figure. So the figure shows the modern petrol engine. So in terms of analysis to determine the performance of the petrol engine or spark ignition engine, so we need to consider a single cylinder and also the air standard assumption, because we want to simplify our analysis and also our calculation for the petrol engine. Okay, so thus after we consider air standard assumption, in order to analyze the process, the performance for the petrol engine or spark ignition engine, we will use ideal Otto cycle. So for the next slide, we will discuss about the ideal Otto cycle in terms of processes, equation, and so on. Okay, for ideal Otto cycle, so the ideal Otto cycle actually is the specific thermodynamic cycle for spark ignition engine or for petrol engine. So in order to describe the process inside the combustion chamber for the spark ignition engine, we need to consider PV diagram and also TS diagrams, where PV diagram will describe the pressure change and also volume change inside the combustion chamber, and TS diagram will describe the temperature change and also the entropy change inside the combustion chamber. Okay, now if you look at both diagrams, the process will involve different states: state number 1, state number 2, state number 3, and also state number 4. And for the Otto cycle, we also will involve 4 different processes. So if you look at the PV diagram, for process number 1, start from state number 1 to state number 2, the process will involve isentropic process. So if you look at the PV diagram, the volume will be decreased from BDC to TDC due to the compression process, and we can see that the pressure increased from P1 to P2. Okay, so if you look at the TS diagram, from state 1 to state 2, there will be the temperature increase from T1 to T2, and during the process, because process isentropic, the value of S2 will be equal to S1. For process number 2, start from state number 2 to state number 3. If you look again to the PV diagram, so during the process we have drastic increase of pressure from P2 to P3, which is due to the heat addition process that represented by Q in this process. So during the process also the volume is constant, where the volume is maintained at TDC. Okay, so if you look at the S diagram for the second process from state 2 to state 3, so we have the increase of temperature. Due to the increase of temperature, the entropy value also increase. Okay, next, so for process number 3, from state number 3 to state number 4, the process will involve isentropic process, and we can see from PV diagram the volume increase from TDC to BDC. Okay, and the pressure during the process is decreased due to the expansion process from P3 to P4. So if you look at the S diagram, for process number 3, the value of entropy is constant because the process involves with isentropic, S3 equal to S4, and during the process also the temperature reduced from T3 to T4. Okay, for the last process from state 4 to state 1, if you look again at the PV diagram, the volume during the process is constant at BDC, and we have heat rejection process where the pressure during this final process reduce. However, if you look at the S diagram, the temperature also reduce, and simultaneously the entropy value also reduce. Okay, so that's how we explain the process of the Otto cycle by using PV and also TS diagram. Okay, now in order to visualize the process, each process in the Otto cycle, so we need to consider a piston cylinder device, a simplified piston cylinder device as shown in the figure. So this figure or schematic diagram already simplified based on the air standard assumption, where we assume that the air circulated in a closed loop. That's why in the cylinder we have air instead of a fuel plus air mixture. Okay, we only consider air inside the cylinder, and the system we consider as a closed system. So that's why we don't have any what I call inlet for the intake valve, and also any outlet for the exhaust valve. Okay, and also for certain processes such as the first figure, the process is the system is well insulated. Okay, as shown in the figure, the surrounding of the cylinder is the insulator, and we assume that the process is quasi-equilibrium, where we assume the movement of the piston is in very slow motion. Okay, now in order to explain the first process, we refer to the first schematic diagram. So the first process, process A, we call isentropic compression. So isentropic because the value of S2 equal to S1, and we call compression because during the process the piston move upward, and the piston will compress the air inside the cylinder, where the pressure and also the temperature will increase during the process. So we have insulators surrounding the cylinder because we will not allow any heat transfer to surrounding or any heat transfer to the air inside the cylinder, because during the process no Q in, no Q out involved. Okay, for the second process, we call the process B as the V constant heat addition process. So V constant because during the process, if you look at the schematic diagram, so no insulator surrounding the cylinder because you want to allow heat transfer process. So V constant because during the process the piston is at TDC, okay, at TDC, and the piston doesn't move. The volume will be constant at TDC, and we have heat addition process because no insulator surrounding the cylinder, so the process will allow heat transfer in to the air. So we have heat addition that represented by Q in during the process. Okay. The third process we call the process C is describe the isentropic expansion process. So isentropic because the value of S3 equal to S4, and during the process we have expansion process where the volume of air inside the cylinder increase, the piston move downward, okay, due to the high pressure and also high temperature during the after the heat addition process. So the piston will move downward, the volume will increase, the temperature will reduce, and also the temperature and also the pressure will reduce. So we have insulator surrounding the cylinder because the process not involve any Q in and so Q out during the process. Okay, so because we not allow any heat transfer during the isentropic expansion process. Okay, the final process, process D, we call V constant heat rejection process. So V constant because the piston is at constant position at BDC, and we don't have any insulator surrounding the cylinder because we want to allow heat rejection that represent by Q out. Okay, so V constant, we call V constant and heat rejection process for the final process. Okay, these are the process or the schematic diagram that can be used to describe or visualize the processes inside the Otto cycle, for the Otto cycle. Okay, so if we relate the process, the ideal process for the Otto cycle with the actual cycle, the actual process in the engine, process A actually represent the compression stroke, where during the process intake valve IV and also EV exhaust valve are closed. Okay, and process B, V constant heat rejection, actually represent the combustion process. Okay, the combustion process. Process C, isentropic expansion, will represent the expansion or power stroke process in the actual engine. And the last one, V constant heat rejection, will represent the process after the expansion and just before the exhaust stroke process. So all these processes in actual engine will not involve any opening of intake valve and also exhaust valve. All both intake valve and also exhaust valve are closed during the process. So our assumption is valid when we consider the system or schematic diagram considered as a closed system. Okay, so that's how we can use this schematic diagram of cylinder piston device to describe the process in the process for the Otto cycle, ideal Otto cycle. Okay, the analysis for the ideal Otto cycle. So when we discuss about the analysis, actually we want to determine the equation, the specific equation that involves the Otto cycle process. Okay, so we just recall back what we have learned before. So for the Otto cycle, we have 4 different processes as described by the schematic diagram. So we have the schematic diagram for the isentropic compression process, and then we have the second one, we have V constant heat addition process. The third one, we have isentropic expansion process, and the last one, we have V constant heat rejection process. And the process will keep continue in cycles. So in order to describe the process, what happened inside the combustion chamber in terms of pressure, volume, temperature, and also entropy, we can use PV diagram and also TS diagram as we described before. So for analysis, so because the the Otto cycle will involve this energy transfer, So we need to use the energy balance equation in order to determine the energy that involved with each process in the Otto cycle. Okay. Okay, so the aim of the usage of energy balance equation, we want to determine the value of Q in and also Q out for the Otto cycle. Okay. Okay, for example, we want to determine the heat transfer value that refer to Q in and also Q out that involve with process number 2 and also process number 4. Okay, process number 2 from state number 2 to state number 3 that involve Q in, process number 4 that involve with state number 4 to state number 1 that involve the value of Q out. Okay, so for Q in, the value for Q in will be equal to, the formula for Q in is equal to U3 minus U2, the internal energy difference. Okay, why we get this kind of formula for Q in? So actually we implement the energy balance equation for the specific schematic diagram. So for Q in, we need to refer for the schematic diagram for the second process for V constant heat radiation, because in the schematic diagram the process will involve Q in. Okay, if you look at the schematic diagram, when we implement energy balance equation, we can see that during the process the piston doesn't move, so no W in, no W out will involve, and during the process also no Q out involved during the process, so we can eliminate the term for Q out, W in and also W out, and so the remaining term for the energy balance equation is only Q in and also delta U. So that's why we have the formula for Q in equal to U3 minus U2, U final minus U initial for the process. Okay, similarly for Q out, we have Q out equal to U4 minus U1. So if we want to determine the formula of Q out, we need to implement energy balance equation to the schematic diagram or the cylinder piston device for the final process of V constant heat rejection process. So if we refer to the schematic diagram for V constant heat rejection process, the piston doesn't move during the process, so no work in, no work out, and at the same time we don't have any Q in, but we have only Q out parameter. Okay, so the remaining term in the energy balance equation is only Q out and also delta U. So that's why we have Q out equal to U4 minus U1. Okay. Okay, next. Okay, so now, as I mentioned before, we have for the internal combustion engine analysis, we have two cases. First case is for variation of specific heat with temperature, and second one is a constant specific heat with temperature. Okay, so the formula that involves with Q in, Q out, that involves with internal energy difference, these two equations actually is used for the first case, which is the variation of specific heat. So we need to use what we call the ideal gas of air table to determine the value of U1, U2, U3 and also U4. However, if the case involves is the constant specific heat with temperature or cold air standard assumption case, so we can use this formula where we just replace, for example, for Q in we just replace U3 with T3, U2 with T2, and we add additional constant value parameter of CV, which is referred to the constant specific volume at constant specific heat at constant volume, because during the process we have constant volume process for Q in. And for Q out also we just replace U4 with T4, U1 with T1, and we add the term for CV. Okay, so Q in equal to CV multiplied by T3 minus T2, Q out equal to CV multiplied by T4 minus T1. So the last two equations actually just for the second case, which is referred to the cold air standard assumption or for the case with where the constant specific heat is the temperature. Okay, next, for the isentropic process, especially for process number 1, start from state number 1 to state number 2, and also the process for the process number 3 from state number 3 to state number 4 that involve the isentropic process. So this equation just for the process that involve this isentropic process. So we cannot use this equation for the other what I call the process that is not isentropic. So we have this ratio V1 divided by V2. Small v represent the what I call the specific volume. The unit will be meter cubic per kg. So V1 divided by V2 actually is represent the compression ratio. We call the ratio as the compression ratio. And VR in the equation refer to the relative volume, and we can get this value from the ideal gas of air table. And this parameter of VR will have no unit. Okay. So if you look individual value, V1 actually not equal to VR1. However, the ratio of V1 divided by V2 will be equal to VR1 divided by VR2. Okay. So because what I call the value of V3 equal to V2 and V4 equal to V1 during the Otto cycle process, so we have this relationship where V1 divided by V2 equal to VR1 divided by VR2 equal to VR4 divided by VR3 equal to V4 divided by V3. So we can use this relation for isentropic process, and the first equation for the isentropic process is only for the first case, which is the variation of specific heat. Okay, but if the case involved is the constant specific heat or cold extended assumption, so we can use this equation. We have temperature ratio equal to volume ratio power of K minus 1. The value of K normally given, and for air normally the value will be 1.4. Okay. Similarly, we have the equation for pressure ratio and also volume ratio power of K. So we have temperature ratio equal to volume ratio power of K minus 1. However, for pressure, we have pressure ratio equal to volume ratio power of K. Okay, so remember that. Okay. Okay, so so next, okay, so you need to remember that. So you have you have two different cases, and you need to implement what I call the correct equation for the correct cases. Okay, now we have the gas law equation, and this gas law equation we can use because we assume that the air inside the cylinder is an ideal gas. So that's why we can use the gas law equation, and we can implement this gas law equations for all states, state number 1 until state number 4. So we can use PVT equal to constant formula. We can use PVT formula for different states, for two different states, and also we can use PV equal to MRT. P stands for pressure, V, capital letter V, stands for volume, M stands for mass, R stands for gas constant normally given, and T represent the value of the value for the temperature. Okay. Okay, and you need to remember that for gas law equation, the temperature must be in Kelvin. Okay, now about the thermal efficiency. So we can use the what I call the general formula for thermal efficiency, where mu Th equal to W net divided by Q in. However, because in Otto cycle, the parameter that we obtain only Q in and also Q out, so we can use the second one, the second equation, where mu Th equal to 1 minus Q out divided by Q in. Okay, so this is the general equation. However, if we consider the cold extended assumption or constant specific heat case, we can use alternative formula for thermal efficiency, where mu Th equal to 1 minus 1 divided by R power of K minus 1. R stand for the compression ratio, V1 divided by V2. Okay, about the compression ratio, R equal to Vmax divided by Vmin equal to V1 divided by V2, capital letter. So capital letter represent the volume, where the unit will be meter cubic. Also equal to V1 divided by V2, small letter, and the unit will be meter cubic per kg for capital letter of small letter of V, meter cubic per kg. Okay, so this is the formula for compression ratio. And if you want to look the effect of compression ratio to the thermal efficiency, so we need to refer to the thermal efficiency formula for the cold air standard assumption. Okay, so if the value of compression ratio increase, in theory the value of thermal efficiency will increase. Okay, so that's good for the performance for the Otto cycle. However, in actual condition, actual engine, we need to limit the value of R, because if the value of R too high, this condition will cause auto ignition and also engine knock. So this phenomena we need to prevent for the actual operation of the petrol engine or the spark ignition engine. Okay, so these are the formula or equation that can be used to analyze the Otto cycle, and also can be used to determine the thermal efficiency for the Otto cycle. Okay, example 2.2. An ideal Otto cycle has a compression ratio of 8. At the beginning of the compression process, air is at 100 kPa and 17 degrees Celsius, and 800 kJ per kg of heat is transferred to air during the constant volume heat addition process. Accounting for the variation of specific heat of air with temperature, determine A, the maximum temperature and pressure that occur during the cycle, B, the net work output, C, the thermal efficiency, and D, the mean effective pressure for the cycle. So for this example, remember that we have two cases involved, two cases for the IC engine analysis. So now for the example, you need to account the first case, which is the variation of specific heat of air with temperature, which means in order to solve the problem, you cannot use the formula involving CV and also CP. So you need to use the ideal gas of air table to determine the parameter before you obtain the correct answer for the question. Okay. Okay, the solution for example 2.2. First, we need to draw a PV diagram and put whatever data given in the question on the PV diagram. So we know that the value of P1 equal to 100 kPa and V2 equal to V3 equal to 1 over 8 multiplied by V1. So this value we can obtain from we can manipulate what we call the value given for the compression ratio, where the compression ratio given in the question is equal to 8. And we know that for the Otto cycle, V1 equal to V4, and the question asks you to determine T maximum and also P maximum. Okay, in order to determine the temperature for T maximum and also P maximum, so we need to refer to both figures or diagram, PV and also TS. So from the both diagram, from PV diagram, we can determine that the value of P maximum actually equal to P3, and if we base to TS diagram, we can determine the maximum temperature refer to the value of T3. Okay, and next question asks you to determine the value of W net, thermal efficiency, and also MEP. Okay, now we continue with the solution for example 2.2. So question A, you need to determine the maximum temperature and also the maximum pressure, which is referred to the T3 and also P3 respectively. So before that, it is better if you can determine the important value for each state. Okay, so now let us determine what we call the important value for state number 1. So the data given for state number 1, P1 equal to 100 kPa, T1 equal to 17 degrees Celsius, which is also equal to 290 Kelvin. And from the data, term of temperature, so then we need to refer to the what we call ideal gas of air table, because now the problem will involve this the first case, which is the variation of specific heat with temperature. So you need to use the ideal gas of table, and you cannot use the equation involved with CV and also CP, as I mentioned before. Okay, now from the table of ideal gas of air table, refer to the temperature 290. From the temperature, we can determine directly from the table the value of U1. Okay, where U1 equal to 206.91 kJ per kg. And also you can determine the value of VR1, 676.1 without unit. Okay, so VR, relative volume, relative specific volume, we don't have any unit. So we need to know the value of VR1, because later on we will manipulate the value of VR1 and also the compression ratio formula in order to determine VR2 for state number 2. Okay, so done for state number 1. For state number 2, will involve with the isentropic process. So we can use any what I call equation involved with isentropic process. So for state number 2, no P2, no T2 given, no pressure, and also no temperature given for state number 2. And also we don't have any value for VR2. However, we can manipulate VR1 value for state number 1, and also the what I call the compression ratio value that given in the equation, where we know that VR1 divided by VR2 equal to V1 divided by V2 equal to R equal to 8. So from the equation, rearrange the equation, so you get the value for VR2, where VR2 equal to VR1 divided by 8, and we get the value of 84.52 for VR2. Okay, to determine the other what I call important value for state number 2, so we need to use the ideal gas of air table. Okay, so you need to find out where is the location at the table for VR2 equal to 84.52. So by referring to the table, the value of VR2 is in between 81.9 and also 85.34, which means you need to make interpolation to determine the others properties such as internal energy, temperature, and so on. Okay, by interpolating the value of VR and also temperature, so you will get the value for T2, where T2 equal to 652.4 Kelvin. And interpolating the value of VR and also the internal energy U, so you can determine the value of U2, which is equal to 475.11 kJ per kg. Okay, so next for state number 2, we don't have any value for P2, so we need to determine the pressure for state number 2, where P2 is unknown at this moment. So the value of pressure we cannot obtain directly from the table of ideal gas of air table. Okay, however, for any state in the Otto cycle, we can implement the gas law equation, PVT equal to constant, or for different states we can use this equation for state number 2 and also state number 1. P2 V2 divided by T2 equal to P1 V1 divided by T1, as shown in the slide. So rearrange the equation, so you'll get the equation for P2, where P2 equal to P1 multiplied by V1 divided by V2 multiplied by T2 divided by T1. Okay, so we have the value for P1, T2, and also T1. The value for V1 divided by V2 actually represent the value of compression ratio, which is equal to 8. So substitute all the value that we have into the equation for P2. So now we will get the value for P2, which is equal to 1799.7 kilopascal. Okay, so done for state number 2. So now for state number 3, if we can solve state number 3, Actually, we already answer what I call the question A, because the question A asks you to determine the maximum temperature and maximum pressure, which is refer to the value of T3 and also P3 respectively. Okay, so now we don't have any information. However, in the question we have the value of Q in, which is equal to 800 kJ per kg. So we can manipulate the equation involved with Q in to determine what I call certain value, in order certain value to use the value for the ideal gas of air table in order to determine the other value for state number 3. Okay, because for ideal gas of air table, at least you need to have one data. If you have one data, you can determine the rest of the other value in terms of thermodynamic properties such as temperature, internal energy, relative volume, and so on. Okay, so now we know that Q in, based on the formula, Q in equal to U3 minus U2. Q in already given, U2 we already calculate for state number 2, and then if you rearrange the equation, we can determine the value of U3, internal energy for state number 3, where U3 equal to Q in plus U2, which is equal to 1275.11 kJ per kg. Okay, based on this value for U3, and also we refer to the ideal gas of air table. So find out the value of U3 in the table. So U3 in the table is in between the value of 1260.99 and also 1279.65, which means you need to make interpolation between internal energy U and also temperature. You can obtain the value for T3, 1575.1 Kelvin. Okay, so we already solved the maximum temperature. And interpolation between internal energy with relative volume. So we'll get VR3 equal to 6.108. So the value of R3 will be manipulated in order to determine the properties for state number 4. Okay, next, the maximum pressure that refer to P3 for state number 3. So we cannot get the what I call the value of P3 by using the ideal gas of table. So then we can manipulate the gas law equation, where for state number 3 and also state number 2, P3 V3 divided by T3 equal to P2 V2 divided by T2. Okay, rearrange the equation, so we'll get the equation for P3, where P3 equal to P2 multiplied by V2 divided by V3 multiplied by T3 divided by T2. So we already have the value for P2, T3, and also T2 from the previous calculation. However, we don't have the value for V2 divided by V3. But for the Otto cycle, we know that the value for V2 is equal to V3. So the ratio of V2 divided by V3 actually equal to 1. Okay, substitute all the value that we have. So we'll get the value for P3, the maximum pressure for question A, where P3 equal to 4.345 megapascal. Okay, done for state number 3, state number 2, and also state number 1. So now the final state is state number 4, where state number 4 will involve the isentropic process. So we can use any equation that involve for the isentropic process. So no pressure and no temperature given for state number 4. So P4, T4 is unknown. So we need to determine VR4 by manipulating the value of VR3 and also the compression ratio value that given in the equation. Okay, so we know that V4 equal to V1 and also V3 equal to V2. So VR4 will be divided by VR3 equal to V4 divided by V3 equal to V1 divided by V2, which is equal to the compression ratio equal to 8. So the value already given in the equation. So rearrange the equation, you will get the value for VR4, which is equal to 8 times VR3 equal to 48.864. By referring to VR4 value and also the other case of air table, find out where the location of VR4 in the table. So the location of VR4 is in between 48.08 and also 51.64. So you need to make interpolation. So interpolation between VR value and also temperature value. So we will get the value for T4, which is equal to 795.6 Kelvin. And also you can determine the value of internal energy. U4 equal to 588.74 kilojoule per kg. Okay, that's how you can determine the important value for each state in the Otto cycle. Okay, so we already solved the important the important parameter or important value for state number 1 until state number 4 for the Otto cycle. Okay, the solution for question B, the network output. So we know that the formula for W net equal to Q in minus Q out, where Q in value already given, which is equal to 800 kJ per kg. And now we need to determine the Q out value, where we need to manipulate the formula for U1, which is equal to 206.91 kJ per kg, and also the value for U4, which is equal to 588.74 kJ per kg. So from this value we can determine the value of Q out, where Q out equal to U4 minus U1 equal to 381.83 kJ per kg. Okay, so from Q in also Q out value we can determine the value of W net. W net equal to Q in minus Q out equal to 418.17 kJ per kg. Okay, now question C, the thermal efficiency. So we can use the general equation for thermal efficiency, where mu TH equal to W net divided by Q in. W net we already calculate, Q in already given, so substitute the value into the equation. So the thermal efficiency for the Otto cycle equal to 0.523 or 52.3%. Okay, the last question, we need to determine the mean effective pressure for the cycle. So we know that MEP equal to W net divided by V1 minus V2. So W net we already calculate. However, the individual for specific volume for V1 and also the specific value for V2 are not available. However, we have the value for compression ratio, where specific volume V1 divided by specific volume V2 equal to 8. So by using the compression ratio equation, we can replace the V2 terms with certain equation, and by replace the V2 value with the we rearrange the equation for the compression ratio. So we will get the value for MEP equal to W net divided by V1 multiplied by 1 minus 1 divided by compression ratio. Okay, however, we don't have the value for specific volume V1, but we can determine by using a gas law equation, which is PVRT formula. Okay, if we rearrange the PVRT formula, we will get the equation for V1, which is equal to R gas constant T multiplied by T1 divided by P1. T1 already given, P1 already given, R gas constant normally given, which is equal to for air, R equal to 0.287 kilopascal meter cubic per kg Kelvin. Okay, substitute the equation into the equation whatever value that we have. So V1 will be equal to 0.832 meter cubic per kg. Okay, so now we can determine the value of MEP. So substitute the value that we obtain into the equation. So the MEP value will be 574 kilopascal. Okay, so we'll answer all the question for example 2.2. Okay, next we go to the example 2.3. So figure 1.1 and figure 1.2 are PV diagram and also TS diagram for an ideal Otto cycle respectively, considering variation of specific heat with temperature, and according to the data given in the both figures, determine A, the compression ratio of the cycle. B, the beginning and the end temperatures of the heat addition process in the cycle. C, the temperature at the end of the isentropic expansion process. D, amount of heat transfer to the cycle. And E, the thermal efficiency. So if you look the difference in terms of question pattern compared to the example 2.2, in example 2.2, the data already given inside in the questions in terms of data. However, for example 2.3, all the data given by the question actually provide in the figure 1.1 and also figure 1.2. So you need to extract all the data from the figures provided in this question, okay, such as pressure, temperature, volume, and so on. Okay, by referring to the figure, you need to answer the question. Okay. Okay, the solution for example 2.3, question A. So you need to determine the compression ratio, R value, where we know that from the formula R equal to V1 divided by V2, volume 1 divided by volume 2 equal to relative volume 1 divided by relative volume 2 equal to specific volume 1 divided by specific volume 2. So if you refer to the what I call the figure 0.1 and also figure 0.2, we can determine the value for V1 and also V2, which is V1 equal to 600 centimeter cubic and V2 60 centimeter cubic, and we will obtain the value of compression ratio will be equal to 10. Okay, next, the beginning and end temperatures for heat addition process. So we need to refer to the what I call the heat addition process. We need to know which state refer to the beginning of heat addition process, and also which state refer to the end state for the heat addition process. Okay. Okay, so now let us determine the important value for state number 1 and state number 4. So we know that for state number 1, the temperature given is T1 equal to 300 Kelvin based on the figure 1.1 and also figure 1.2. So from the temperature, we need to refer to the ideal gas of a table, because the problem involves with in the question mentioned about the case number 1, where we need to involve the case for variation of specific heat with temperature, which means we need to use the ideal gas of air table. So we cannot use the equation involved with Vc and also Vp. Okay, so from the temperature, we can obtain directly the value of U, where U1 equal to 214.07 kJ per kg, and also we can obtain the value of for the VR1 equal to 621.2. Okay, for state number 2, involved with Isentropic process, and also P2 already given in the figure, where P2 equal to 2433 kilopascal. Okay, so for state number 2, in order to obtain the other parameter for state number 2, we need to determine VR2. So for VR2, we can manipulate the value of VR1 and also compression ratio that we obtain in question A. So we know that R, compression ratio, equal to VR1 divided by VR2 equal to 10. Rearrange the equation, we will get the value for VR2. VR2 equal to VR1 divided by 10 equal to 62.12. So from the value of VR2, use the ideal gas of air table. So we can make interpolation to determine the other parameter for state number 2, where interpolation between VR and also internal energy U, we can obtain the value of U2, where U2 equal to 536.10 kJ per kg. Okay, so next, interpolation between VR and also T, temperature, we can obtain the temperature for T2, 730 Kelvin. Okay, for state number 3, the pressure also already given. No need to calculate the pressure for P3. So P3 equal to 4867 kilopascal. Okay, so now for state number 3, we don't have any other, what I call, any other information, so we can use the ideal gas law equation, or ideal gas equation, P2 V2 divided by T2 equal to P3 V3 divided by T3 in order to determine the temperature for T3. Okay, so rearrange the equation, so we get T3 equal to T2 multiplied by V3 divided by V2 multiplied by P3 divided by P2. So we already have the data for P3, P2 and also T2. However, we know that V3 equal to V2, so now the ratio of V3 divided by V2 equal to 1. So from the equation we can determine the temperature for state number 3, T3 equal to 1460 Kelvin. Okay, and by referring to the ideal gas oxide table and also the temperature that we already calculate for T3, so T3 you can obtain directly the value of what I call the internal energy U3 from the table, where U3 equal to 1168.49 kJ per kg, and also we can determine the value of VR3 directly from the table, which is equal to 7.801. Okay, so now actually for the process, the beginning and end as temperature for heat addition process actually refer to state number 2 and also state number 3, because state number 2 until state number 3 involved with heat addition process. So the beginning of the heat addition process refer to state number 2, and the end process for the heat addition process is referred to state number 3. So we already determined T2 and also T3. So we already solved the problem for question B. Okay. So next, for question C, the temperature at the end of the isentropic expansion process. So this state actually, this condition actually refer to state number 4. Okay. So analyze state number 4. State number 4 will involve isentropic process. So we can use the formula involved in isentropic process, and we can determine VR4 in order to determine the other value for state number 4. So VR4, we can manipulate the compression ratio formula, where we know that VR4 divided by VR3 equal to V4 divided by V3, and V4 equal to V1, V3 equal to V2. So the ratio for V4 divided by V3 actually equal to V1 divided by V2. That represent the compression ratio value, which is equal to 10. So rearrange the equation, so we get the value for VR4, which is equal to 78.01. Find out the value in the ideal gas of air table. So you need to make interpolation between VR value and also internal energy value U. So you can determine, or you can obtain the value for U4, which is equal to 490.32 kJ per kg. And then you will get the answer for question C, the temperature of T4. Okay, so interpolation between VR and also temperature, we can obtain the value for T4, which is equal to 671.93 Kelvin, which is represent the value of temperature at the end of isentropic expansion process. Okay. Okay, next. Okay, the solution, we continue with the solution for example 2.3. We need for question D, we need to determine the amount of heat transfer to the cycle, which is referred to the value of Q in, because heat transfer to the cycle. If the question asks you about the heat transfer to the surrounding, so you need to calculate the value of Q out. So now for this question, for question D, you need to determine the value of Q in. So we know that the formula for Q in for the Otto cycle is equal to U3 minus U2. So we ought to calculate or determine the value of U2 and also U3. So easily we can determine the value of Q in, which is equal to U3 minus U2 equal to 632.39 kJ per kg. So substitute the value of U2 and also U3 into the equation. So we get the value for Q in equal to 632.39 kJ per kg. Okay, next we need to determine the thermal efficiency. So we can use the formula for thermal efficiency. So we have two general thermal efficiency, where thermal efficiency equal to W net divided by Q in, or thermal efficiency equal to 1 minus Q out divided by Q in. So we know that Q out equal to U4 minus U1, Q in equal to U3 minus U2. So the value of U1 until U4 we already determined previously. So we just substitute all the internal energy value into the thermal efficiency equation. Okay, so these are the value for internal energy that we already obtained: U1, U2, U3, and also U4. Okay, substitute into the equation. So you will get the value for thermal efficiency for the Otto cycle, which is equal to 0.5632 or 56.32%. Okay, that's how we answer the example 2.3 when involved with variation of specific heat with temperature. Okay, example 2.4. Explain on how the ideal Otto cycle differ from the ideal diesel cycle, then show the difference on the PV diagram for both cycles. That's for question A. Question B. An ideal Otto cycle uses air as the working fluid. The minimum and maximum temperature in the cycle are 300 Kelvin and 1340 Kelvin. The volume before and after isentropic compression process are 0.0048 meter cubic and 0.0006 meter cubic respectively. Assume constant specific heat at room temperature. Determine 1. The compression ratio of the cycle. 2. The amount of heat transfer during the heat addition process and also heat rejection process. Number 3. The thermal efficiency. Take air in terms of CV value equal to 0.718 kJ per kg Kelvin and K value equal to 1.4. So if you look at the figures, if you look at this question will consider case number 2, where you need to consider the constant specific heat at room temperature or cold air standard assumption. So now for this question you cannot use the ideal gas of air table, so you need to use the equation involved with CV and also CP. Okay, so another clue that you can use in order to determine the cases is the question gives you the value of CV equal to 0.718 kJ per kg Kelvin and also the value of K equal to 1.4. Okay, so if this kind of data given in the question, automatically you know that the question will ask you to consider the cold air standard assumption, where you need to use CV and also CP formula, and you cannot use the ideal gas of air table for to solve the problem. Okay, so now in terms of solution, I will discuss the solution for question B that involves calculation. So question A you can answer by yourself by looking at your textbook, or you can just Google what I call through the internet. Okay. Okay, solution for example 2.4. Question B1. So you need to determine the compression ratio. So this question is easy, where we know that compression ratio equal to V1 divided by V2 equal to VR1 divided by VR2 equal to specific volume 1 divided by specific volume 2. And we know that the value V1 already given in the question, where V1 equal to 0.0048 meter cubic and V2 equal to 0.0006 meter cubic. You just substitute the value into the compression ratio formula, so we will obtain the value of compression ratio, which is equal to 8. Okay, next question B2, where you need to determine the amount of heat transfer during heat addition, which is represent the value of Q in, and also the amount of heat transfer during heat rejection, which is referred to the value of Q out. So now you need to determine the value of Q in and also Q out. So before that, you need to determine the important parameter for each state involved with the Otto cycle. Okay, Okay, so now before we continue, remember that the question for example 2.4 involves the second case, which is referred to the constant specific heat case or cold extended assumption case. So you cannot use the ideal gas of air table. So what you have to use to solve the problem, you need to use the formula involving CV and also CP that we have learned before, and also you can use what I call the equation for the gas law, and also the equation involved is cold extended assumption. Okay, for state number 1, so the main parameter that we need to determine for each state is the temperature. Okay, are the temperatures. For state number 1, T1 already given, where T1 equal to 300 Kelvin. So this value already state in the question. Okay, for state number 2, will involve the isentropic process, so we can use the cold extended assumption equation for isentropic process. For example, we can use this equation: the temperature ratio equal to volume ratio power of K minus 1. So the value of K, the equation already provide the value of K, which is equal to 1.4 for the air. Okay, so now we need to determine the temperature of T2. Rearrange the equation, so we'll get T2 equal to T1 multiplied by V1 divided by V2 power of K minus 1. And this equation also equal to T1 multiplied by R power of K minus 1. So V1 divided by V2 actually equal to the value of R, compression ratio. So substitute all the value that we have, and remember this equation in terms of temperature, the value must be in Kelvin. Okay. Okay, so now you get the temperature T2 equal to 689.2 Kelvin. Okay, so now for state number 3. For state number 3, the temperature T3 also already given in the question, which is equal to 1340 Kelvin. And state number 4, because state number 4 will involve the isentropic process, which is for the process involving state number 3 and also state number 4. So we can use the equation for isentropic process for the cold extended assumption. So we have T3 divided by T4 equal to V4 divided by V3 power of K minus 1. So rearrange the equation, so we get the equation for T4, and this equation also equal to T4 equal to T3 multiplied by 1 divided by R power of K minus 1. Okay, substitute the value, so you obtain the value for T4 equal to 583.3 Kelvin. Okay, now in order to determine Q in, Q out, so you need to use the value of CV and also the value of CV, where the the CV equal to 0.718 kJ per kg Kelvin, the value of K equal to 1.4. Okay, now we know that the formula involves Q in based on the cold extended assumption, or based on the constant heat case with temperature. So Q in equal to CV multiplied by T3 minus T2. So we have the value for CV. T3 we already obtained, and also T2 we already calculate. So easily we can determine the value of Q in, where Q in equal to 467.27 kJ per kg. And for Q out, formula for Q out equal to CV multiplied by T4 minus T1, which is equal to 203.3 kJ per kg. So for question B already done, because we already calculate the value for Q in and also Q out without use any ideal gas of air table. Okay, so now question C, last one, we need to determine the thermal efficiency. So we can use the formula for thermal efficiency, where we have thermal efficiency equal to W net divided by Q in, or we can use 1 minus Q out divided by Q in. We already calculate Q out and so Q in. Just substitute all the value of Q out and so Q in into the thermal efficiency equation. So we'll get the value of thermal efficiency equation for this Otto cycle equal to 0.5649 or 56.49%. Okay, so this is the example. The problem involved with constant specific heat case. Okay, for your exercise, in order to check your understanding about the Otto cycle, please answer this question. So I will not provide the solution, so you need to find out the solution by yourself. So actually this question that come from the what called the past final exam question. Okay, so the figure shows a spark ignition engine operating on the ideal Otto cycle. The movement and the distance of the piston from the top dead center TDC and different conditions are shown in the figure. The cylinder of the engine has a bore size of 10 cm. The isentropic compression process begins at 100 kPa and 25 degrees Celsius. The temperature at the end of the isentropic expansion process is 5 to 7 degrees Celsius. Accounting the variation of specific heat with temperature, determine A. the compression ratio of the cycle, B. the highest temperature in the cycle, C. the amount of heat transfer to the cycle, D. the thermal efficiency of the cycle, and E. draw the PV diagram for the cycle. Okay, so if we look in this question, the data of the question given in the question, and also you need to extract from the figure provided for the question. Okay, so you need to recall again the basic concept of certain terminology that you use for reciprocating engine. Okay, so try to answer this question. So if you want to know the solution, you can discuss with me. Okay, so that's all I think for this part, the discussion for the Otto cycle. Next we will discuss about the diesel cycle, the thermodynamic cycle for the diesel engine. Okay, Assalamualaikum.